space. And this is the title, but I mainly talk about how we can construct a virtual cycle of moduli of sheaf on Calabi Yau fourfold. Let's start with a review of Richard talk yesterday. First part I want to review is how we define virtual cycle from maybe our fantasy. This fantasy.
It's called Thomas fantasy, by the way.
Yes, it's Korean. And yeah, you have to be very polite. So this fantasy is picture. Actually, we are interested in some ugly space M, but instead of thinking this, we want to think a nice smooth space and bundle over A and section, which cuts out M. And from this data, A bundle E and section, we define a cone as a limit of graph. And explain this limit is contained in E restricted to M as a space, and let's call this cone as a C. Then virtual cycle was defined to be inverse of term isomorphism. The image of this, of the inverse of this term isomorphism. Then this lies in Chargorov virtual dimension M. Here, yeah.
Also C.
C is this. Limit. Code. Yeah. Yeah. So this virtual dimension was dimension of M A minus rank of B. Okay. So one more thing I want to talk about is if we denote this embedding, maybe this color. If we denote this embedding by J, then the composition of inverse term isomorphism and push forward by this embedding J, that is Euler class of E defined on A. So as an operator, so this is something like this. So for now, I just want to say, assume like Euler class is more familiar object, and yet say this is just a characteristic class. Yeah. Okay. So this starts with this fantasy, so it's not reality. So he also explained in reality how we can get virtual cycles. This reality is definition of Berend-Fantecchi. This reality was morphism of some complex switching -1 and 0 degree, two truncated cotangent bundle such that satisfying two conditions, which one is zeros of zero cohomology is isomorphic to which is so all these technical conditions is actually I don't know what this means. I'll explain what this means. Yes, anyway, we need such conditions. Anyway, if you are given this data called the perfect obstruction theory, then in most cases, locally we have this fantasy, and this is somehow gluing of that's first order linearization.
Sorry, is this only M? Is this literally true?
Or yeah, this is Keller differential of M.
It means that M is non-singular.
M is singular, can be singular. So Keller differential is always defined.
Is it real? This is a sheet.
This is sheaves, yes. Sheaves.
Isomorphic as sheaves.
Yeah. Maybe this is somehow the definition. One is confusing. Then we can glue that locally defined cones, so that we have the embedding from glued cone to the dual of this bundle. Let's denote this by E lower one. Then again we can define virtual class to be the image of inverse form isomorphism of C. Then that's also a class of Chow group. Here virtual dimension is rank of E0 minus rank of E. I should say that this Chow group is some abelian group generated by integral subscheme of M. So yeah, this. Yeah. So we have some similar expression of that last sentence. Let's say J is an embedding of this outside. So here we have embedding of M into C as a zero section, this zero section. Then again, we have Euler Euler class expression of where phi is a projection mode. Any questions?
So the
yeah.
virtual dimension,
Yeah.
this is a single dimension, characteristic class in a singular dimension. In
This one?
VD.
VD is rank of E0 minus rank of E1.
Yes,
Right.
and it's the expected dimension of numbers.
Right. Any questions on review from yesterday? Okay. Then now, this is also review. Let M be a moduli of stable sheet on Calabi Yau topological. Then Huibret and Thomas morphism as they defined, actually they proved there exists a morphism from something to Lm satisfying those two conditions. But it has non-trivial -2-degree term. However, good thing is, but also there exists an isomorphism theta symmetric induced by, so there, although this may have this -2 term, this has this like symmetric property induced by zero duality. And even locally, M is described by this another fantasy. Now E is special orthogonal bundle of rank R with this quadratic form, and S is isotropic section. So now the local model of M is such that three-term complex induced by this model, that is three-term linearization. Isomorphic to a derived cut. So this is local.
Sorry, we're talking about stable sheets and Calabi Yau.
Yeah.
So you haven't given a name to the Calabi Yau.
Oh, yes.
So it's X.
Okay. Yeah. Okay.
Yeah.
Say this is X.
Then some of these sheets, either and so on, are on X.
Mm-hmm. No. This on N. This
What
morphism.
does M got to do with X? So the
N is
singularity you're using
yeah.
is on X.
Oh, right. Oh, this is induced by seriality of X.
Yes, so that implies that the redoubts are sheets on X with a fullbacks of sheets on X.
What yesterday Richard explained the cohomology of this. This is X I plus 1 of, let's say, at some point F, which is a sheaf on X, maybe. This is Y.
So it's what did we say about M cross X?
Right.
You have a space of things on X parameterized by X.
Yeah.
So you should write M times X projection to X and then use
Yeah.
maybe have
Yeah. So, yeah, we have locally we have this picture of M, this obstruction theory of M. Then now also here let's define virtual dimension is. Where is it?
sorry, another thing with me is you're writing down that complex.
Mm-hmm.
So you have in mind that there's not that it's an exact complex, but that there are zeros. It's a complex of length 3 in the derived category.
Yeah.
And it has those 3 terms and is 0 outside.
It has 0, 2, minus 2.
It's a 0 each
0.
No, it's a 0. It's a complex of length 3.
Mm-hmm.
With no other terms. All
No,
the terms
right.
outside are 0.
Yes, yes.
And that's because X is 4 dimensional.
That's right. Yeah. Okay. From this data, what we want to do is, so first, define virtual dimension is virtual rank of E dot, which means rank of E0 minus rank of E minus 1 plus rank of E minus 2. Then, what we know is this also reviewed. This also reviewable chapter. The Edidin-Graham has defined square root Euler class. Of V. Whose scale is maybe I should say when VD is even up. See, this is special orthogonal bundle of rank 2n. Then Edidin-Graham defined this Euler some characteristic class whose square is this Euler class up to sine. So what we want to do from here is just we use kind of this equation. So then now we want to construct square root of inverse Thom isomorphism satisfying something like this, like that. Then we define
Like to see.
Yeah, we want to try to construct this.
It's a morphism.
This is
A function.
this is a operator from Chia group of dimension like any for any k plus 1 n of actually
And it's the
yeah n is already this rank is 2n. And yeah, I should have said this square root Euler class is already an operator of Edidin-Graham defined such an operator. And you want to somehow localize it to localize our codomain such that it's push forward, composition with the push forward becoming Edidin-Graham's construction. After we construct this, we want to define our virtual cycle to be this class as we did in this the Pateki case. Then this lies in this is a very brief plan. So what we should do is first like this. And also we need to prove sorry, before that. And since we construct this from this, what is it? Local picture. So we also need to explain how we can globalize this picture. from this local picture to go global picture, we need to prove such statement. If we can find a representative of this E in this shape globally, then also we can define our virtual cycle to be scale to Euler class of scale to inverse Thomas morphism. Yes, now this is. Yeah, I should say this virtual dimension is whatever it is, it means dimension A minus okay. And now this is rank of E0 minus. So the second thing we need to prove is this E dot here is actually represented by this symmetric form of system complexes. Okay. And then we have to show it. Ah, okay. Okay. The third thing we have to prove is this construction is independent of the choices of this symmetric three-term complexes. This is brief plan. Do you have any questions so far? Here we have this element in the derived category, and what we want to prove here is this element is actually represented by this some symmetric form of complex. Then yeah, it is. The TA is restricted. Yeah. So I can hear.
The question
No.
is,
The whole construction is not only the functions, linearized.
Yeah. Okay, this is the plan how we construct virtual cycle. The more questions. Okay. Then we start.
some geometric reason why you expect to cause,
Y dimension PD.
Yeah, I already have a question. Somehow, is there something to
Their duality means that the obstruction bundle has a quadratic form, non-degenerate quadratic form. And so we're dealing not with a bundle, but not with a GL2N bundle, but an SO2N. That's the perfect obstruction in dimension form.
Just if we just consider like as band particle, then virtual dimension is not well defined because obstruction jump always twice over the rank of obstruction bundle jumps twice over like this. The shape of isomorphic complex of this is somehow like maybe 8. So this has twice more rank than this K. Yeah.
And square root is really a spinner.
Yeah.
A spinner class.
Right. Okay, now wanna review a definition of a special orthogonal. So let Y be any scheme and E be a bundle over Y. We say it is orthogonal if it keeps with the quadratic form, Q, which is non-degenerate, symmetric, and bilinear. So another interpretation of these properties is because this quadratic form induces morphism from E to E dual, and this non-degenerate condition is Q is isomorphism, and symmetric condition is Q is Q dual. So now this condition looks very much like this duality condition.
Before you were writing so about this thing, so the E is minus 1.
Okay, now I want to explain what this special means. Okay, now let's fix an identification of determinant bundle of E dual to the inverse of this determinant, this line of determinant, this right inverse. Yeah, let's fix this on identification. Then is special orthogonal if in addition there is an isomorphism O from determinant E to OI such that first Q determinant Q composite with I E. This is four types of actually you can say this some non-zero constant. So here, yeah, we have we may choose several conventions of this constant, and also you can maybe choose another convention of this identification. But anyway, if we choose this where, then I should explain later. Anyway, so this special, if this is special orthogonal, means like if it is equipped with this orientation as well.
The orientation is in the brackets over the arrow with one tensor against the other.
Yes, I did. Yeah.
Times
Determinant Q. Here we have this Q.
where does the orientation go? Where's the orientation?
At the end of the sentence.
Right.
So that's a bit confusing because those two things will always be equal for some choice of constant. Okay? You can't choose the constant, right? It's a universal object. It's like 1 or -1 or I. I'm just saying, you specify a constant, not us.
Okay. Yeah.
Does that make sense?
Okay.
Two non-zero numbers are always equal up to a constant. But the constant is something, so that whatever it is, that's one.
Yeah.
That's one.
Okay. Yeah. Then I will choose this -1 to the end. This for okay. This is the definition of a special orthogonal. And now, okay, the lambda is upon the of E, then we say this subbundle is isotropic if Q restrict to lambda is trivial, and it is maximal isotropic rank of lambda is n. Okay. And yesterday, the chart explained us from E, we have this real bundle, ER, whose direct sum is equal to bundle E as an oriented simple bundle. Yes. So this orientation actually, this orientation is designed to be to satisfy here this real positive definite quadratic bundle E is orientable by some orientation such that so what I want to say is this is also orientable, and orientation we can pick orientation satisfying this condition. Then since this is orientable, we can define Euler characteristic in homology. And that gives a Borisov-Joyce virtual class, as explained yesterday. Anyway, this is not our purpose. We want to define what's positivity of the maximum isotropic. Positive. If the isomorphism so this is always isomorphism. This orientation. Then Edidin-Graham defined scalar Euler class of this special orthogonal bundle like this. So first they pick cover. So I should have noted that this positive maximum isotropic may not exist. So what they did is first pick some cover where there exists canonical maximized positive canonical positive maximum isotropic subbundle. And there exists some also class such that push forward is some like Jeongseok Oh homology class of dimension 0 such that this is Then Edidin-Graham defined their skew Euler class by then they satisfy every nice properties. First, this is really scalar of Euler class. And if there exists positive or negative maximal isotropic, then its Euler class is plus minus K-theoretic. So here plus if that is positive and minus if that is negative. And also they satisfy written in some formula. From here, I want to So yeah, thank you. So this is actually coefficient 1/2. So we cannot use just a z coefficient here. Yeah, because this constant comes from here. Okay. And from this Edidin-Graham class, we want to define this for SO and bonded. Okay. Okay. First of all, so since we have this cover where there always exists this canonical maximal isotropic abundant, then we have there we have this exact sequence. Okay. Now, now let's assume which is isotropic section such that isotropic means
And this is after making the cover.
yeah, this is
You using kind of splitting.
right. This is on here. Then we have pullback over this S. Here we have two. Here we have this composition. Okay. And on the zero of S1, we have this S2. S2 may not exist where S1 is not 0, but where this is 0. So since this is 0, so we have this. Okay, then what Kim and is cross-section localization. Tell us I should say, sorry. Let me write it first and explain later. So yeah, okay. First of all, this is a bundle restricted to ZS1. And this morphism is Fulton-Mapperson morphism. Inverse Thom isomorphism to 0 over S1. Then Kim Lee proves there's some smaller, like some factorization of this inverse Thom isomorphism. From this space is because here we have S2 over this space. Yeah, this S2 defines this morphism. So over, if we consider this as a total space, then we can consider this as a function. And let's say this is 0 of this function. So this is a closed 0 over in 0 contained in this total space, and this is and Kim and Lee proved there's such. So where we can define this to be then this is an homomorphism from and solution. This is not enough because we we have to start with the cone. So when we have some like this cone, such that it's tautological. Like if we have this cone, then we have always so this diagonal morphism induces this section, and this is morphism. This is projection from cone to y. Okay, so if we have this, then there is a tautological section always, and if how is isotropic? So we say C is isotropic if this is isotropic. Then we can define this from cone C to its vertex set y. And this satisfies every the good properties of Edidin-Graham classes. And using that property, we can prove virtual class is well defined. Because if we start with the special orthogonal bundle, then they may not have maximal isotropy. This is just we should start with the isotropic section. Then this somehow split into this two sections. So one is just defined by composition, and the other is defined on the 0 over S1. So this co-section is defined from.
So it seems to me that all of this could be done much more neatly using the method of splitting, the splitting principle. When you're working with, if you're trying to work with term classes effective bundles, you say, I can assume that effective bundle splits as a direct sum of line. And you do that just by lifting it to the flag class. Instead of feeding the principal bundle in this space, think of the flag.
Right.
So you can do the same thing for with SM2N, except now the flag is two-dimensional.
SL2N.
Sorry?
Did you say SL2N?
SO2N. We're working with SO2N.
Oh, yeah.
And so you have to do whatever is total flag space, the maximum flag.
Right.
So that would reduce everything to rank 2. Rank 2 SM2. So then it's essentially like maybe I'm wrong. small neighborhood of a point,
Yeah.
then every bundle is just trivial.
Right.
And then it's just copy of the principal bundle SO to X. Right, so then you can split it.
Right. Yeah, locally.
So here we're saying, well, you can't do that globally. You can up to pass into a fabric.
Yeah.
So that's exactly a splitting.
Right. Yeah.
So, you unfortunately didn't have enough time to tell us anything about counting sheets on blood characterize. You spent all your time on establishing that there is a virtual class.
Right.
Are there any cases where you can count classes, count sheets?
So yeah, what I wanted to explain more is using this we could define virtual class. Then over that class we can integrate cohomology insertion. Then we can get an invariant. And also in K-theory, then even though we don't have insertions, we can define invariant. So I wanted. Yeah.
Did you do some computations?
No.
And the invariants will be like, I don't know, like chow with one of the two. Yeah, minus one in the. Like,
Yeah. So
more questions, comments, answers?
I can give you a few counter infinity calculations. Special cases where I want to be able to do that.
but some people computed some invariants.
I always knew that